Hey everybody, this video is about distributed loads as opposed to a discrete load. For example, you have this beam with a roller support on this side, a pin support on this side. A discrete load is like I put like 10 pounds over here, right? Or somewhere else, like 5 newtons, whatever it is, right? And so let's say this is 3 meters and 4 meters. So you could draw the free body diagram, right? And then you're like, okay, there is, I'm just going to pick colors. Okay, so let's say I have coordinates. So there's a roller at A, so that means there's a reaction force this way. Then a pin over here, so there's a 2-dimensional reaction force, which I'm just going to decompose into x and y components. Okay, so these are the reactions at the supports. And then there's this 5 Newton discrete load here. Okay, so what happens if instead of a discrete load, I put a block that's like this big, a block, like a 10 Newton block. It's not, I mean, you can model it like this, but really the force is kind of distributed over this area. So that's where we call it a distributed load. Or let's say I pile some dirt on the beam, like I pile some dirt. So, right, there's more dirt here than there is here. So there's more load here than there is here. So you see, I can kind of make this into slices. And then depending where I am in this x direction, the load changes as a function. So this is a loading curve. So it's a function of position. So it'll be some force per unit distance. So like newtons per meter, or pounds per foot. And here's the big trick, is you can represent this distributed load as a single discrete force. So you're modeling it. So you represent this as one force. The magnitude of this force is the area of this shape. Okay? And then the position of this one force is at the centroid of this shape. So if the centroid is here, at some location here, then that's here. Okay, let's try, it's like short explanation, right? Let's try an example. So let's say we have this bar with a pin here and a roller here, and I have this distributed load. So I can just represent that distributed load. Okay, so I'll model this pin and this roller like this. Coordinates like this. So this looks like a triangle. So I can represent the magnitude by the area of this shape. So what's the area of the shape? 1/2 base times height. So 1/2 8 times 60, so 240. So 240 Newton meters times meters is newtons. And look at this triangle. So what's the area of this triangle? 1/2 base times height. So 120 newtons. Where? At the centroid. So the centroid of this triangle is here, 2/3 of the way over. Right, so here to here is 2/3 of the way over this much. Right, and then how about this triangle? The centroid is 2/3 of the way over this way. 2/3 of 4 meters. So there you go, right? So I represented this distributed load as these discrete forces. Okay, let's try another. Here, like we have this beam with a pin at A, a roller at B. Okay, and then now I want to represent this distributed load. So it looks to me like a triangle on top of a rectangle, and then another triangle over here, right? So let's say this rectangle, the area is 2 times 4, so 8 kilonewtons. And then how about this triangle here? So that looks like 1/2 base times height. So 2 over here, 3 over here. So here to here is 1. So 1/2 base times height would be 2. And then this triangle, 1/2 base times height would be 3. Okay, and then where? So this rectangle, just in the middle. So the rectangle was this one, right? This. So that's 2 meters. For the triangle, it's the centroid is here, which is 2/3 of the way over this much. So here to here is 2/3 of 4 meters. And then for this triangle, here, 2/3 of the way over this way. Okay, right, so this distributed load I represented as these 3 discrete forces. Okay, one more example. Something like this now. So now, right, it's a fixed support at A, so that means there's a 2D force and a couple. And then how do I represent this distributed load? It's just a single force, this much. The magnitude is the area of this shape. And then the position, this, is the centroid of this shape. So all we need to do is find the area and then the location of the centroid. Right, so for the area, you just integrate dy dx, where y goes from here to here. Right, so y goes from 0, which is this, up to this function, which is this. Right, so you just write that here. And then in the x direction, from 0 to 5. Right, and then you can integrate, right? Integral dy is y from 0 to here, so then it's right, and then you just integrate this, and that's the area, and that's the magnitude of this. For the centroid is like this, right? So we got the denominator already, that's this. So for the numerator, we just have to integrate x dA, which you can split into dy dx, and then y from 0 to this, that's this, and then in the x direction from 0 to 5. Okay, all right, and then so you integrate dy becomes y from 0 to this thing, and then times another x over here. Okay, and then just multiply this x through, and then integrate this, and then this is the numerator, right? This is the numerator. This. So you take your answer here, divided by the area, and then that's the location of the centroid. Okay, so give these a try and let me know how it goes. And if you have questions, just post it to the forum. Okay, so I'll see you in the next video.